Okay, let's move on to neural networks. Neural networks are basically inspired by biology, right? When we talk about neural networks in computer science, information science, machine learning, in reality, we are talking about artificial neural networks because the actual neural networks are inside our bodies, right? If you think about how our brains work, there's millions of neurons in our brains of different types, and basically the way a neuron works, a neuron is nothing more than a cell, like the one that you see here, and it has sort of these extensions that are called dendrites. And the way this works is that these dendrites will receive a stimulus or different types of stimuli, and that will be processed by the neuron, and then that processing will generate a specific output, and that output is nothing else than a response. Like, say for example, someone pinches you in your arm, you will jump or you will scream, right? And that's simply because you had this stimulus, which was the pinching, you had the neuron process that information based on prior history, and then that was your reaction. Okay, so when we talk about artificial neural networks, it's exactly that same thing. Keep in mind that it's going to be just an architecture for either classification or regression that's based on the fact that you're going to train how neurons learn to respond to a stimuli. In our case, the stimuli are going to be the input data sets, and the response is going to be basically the classification or the regression. And so today I'm going to be talking about a couple of different things with respect to artificial neural networks. We're going to start with a single neuron, like how do we define a single neuron, how does it work formally, by this inspiration from biology, and also how do we train a single neuron model with what is known as the delta rule. And then we'll move on in a second part to more complex neural networks, so moving beyond one neuron to what we call multi-layer perceptron models. So we will define them, how these are more complex architectures that have multiple nodes distributed across multiple layers, and we will also look at how these models are trained with what's known as feed-forward and backpropagation passes, okay? Again, throughout both single neuron multi-layer perceptron, what I'm going to be talking about is how these models, these artificial neural network models are trained internally by the different packages that you can use in R or in Python or in many other languages, okay? When you will run these packages, you will not be doing any of the delta rule or feed forward or backpropagation. Those are all things that are going to be directly done by the packages, but it's very important that you understand how these things work internally so that, again, when you start working with the packages and with the different variables that you can change within a package, you are aware of the meaning of those parameters, of those variables. So a single neuron model is sort of the simplest neural network that you can think of, okay? And again, as I was saying before, artificial neuron, it's basically, inspired by the definition of an actual neuron in our brains. It's going to be an architecture that receives input signals, which is, our training data. It's processed by the neuron itself, and it outputs a signal. The way these neurons have been defined is that the different input signals are basically applied a weight, and those weights that we apply to the input signal allow us to give more or less importance to that signal. Okay, so in a way, the same way that an actual network learns how to process stimuli, coming from the dendrites, the artificial neuron also learns how to give different importance to different input information so that, we can learn different types of outputs. Okay. And so formally, a single neuron model, you might also, when you read about it, you might also see that it's also called threshold unit. This is sort of the simplest neuron. As you can see here, we have an input. This could be our input data, x1, xn, okay? This is inputted into the neuron, and we apply some weights into that input, right? And then, the neuron does some sort of processing and it outputs a value. Now, how does this processing work? You have it up here. Okay, so the output y is going to be 1 or 0, okay? We'll see how these can also be values beyond binary. Right now we are seeing sort of the simplest case, which is this binary, but we'll see how this can be transformed into continuous values. But basically, the output y will be 1, if after multiplying the input by the weights, we see that that summation is larger than a threshold. Okay? If it's larger than a threshold, the output will be 1. If this product is not larger than a threshold, it will be 0. Again, this is the simplest single neuron model that you could think of with the simplest output, which is a binary output. Now, what can we do with this neuron? Well, we can do certain things, not a lot, but we can do certain things. And the typical example that we give when we talk about a single neuron are Boolean logic examples, right? So for example, the Boolean and, the Boolean implication, these are just, functions that we study in Boolean logic. And so this is just a way of showing how we can use a single neuron to implement these functions. Okay, so a very simple, function that we could implement with a single neuron. So here you see the Boolean conjunction x1 and x2. If you look at x1 and x2 and the y value, what the Boolean conjunction does independently of neural networks, it's just a function that takes these two inputs and outputs a value 1 whenever the two inputs are 1. Otherwise, it outputs a 0. Okay, so this is just a conjunction function that's, studied in Boolean logic, and basically it does what I said. So how can we implement this conjunction function using neural networks? Pretty straightforward. We have an input. The input is multiplied by certain weights, and then we have a threshold. We want to output 1 if the two inputs are 1. We want to output 0 else. For all the other conditions. And so what we do is that we can define something like this, okay? We can apply a weight of 3 to x1, a weight of 2 to x2, and then basically this summation here, if this sum is larger than 4, we'll output 1. If it's smaller than 4, we'll output 0. And this is a way of implementing the conjunction using a single neuron. We can do exactly the same thing with the implication, with the logic implication. The implication is just a function that basically, whenever you have 0 implies 1, the output is 0. Otherwise, the output is always 1. Okay, even if you don't know what an implication is or how it works in Boolean logic, just be aware that what you want to do is basically a function that whenever you input a 0, 1, it's going to output a 0, and whenever you input anything else, it's going to output a 1. So how do you design this? So you have to think about, sort of this way of like these weights, like, what are the weights that you need to apply to the input so that you can actually output zeros and ones as I just described. And so the weights and the threshold could be, for example, 2 and minus 2. And so, if you multiply 2 by x1 minus 2 by x2, then you look at whether that value is smaller or larger than minus 1, right? If the value is smaller than minus 1, you output a 0. If the value is larger than minus 1, you output a 1. So this is just, as you can see, basically what this means is that with a single neuron, we can implement very basic Boolean logic functions, okay? So we cannot do like sort of more complex computations, but they're useful for this type of simple computations. And as you can see, internally what we're doing in reality, when we are training a neural network to do that, is that we are looking for the weights and for the thresholds that will allow us to get the output that we want to get. Right? And this is sort of the most important thing to know about neural networks, right? So you have a set of inputs, that these are the outputs that you want to get. What are the weights and what's the threshold that will get you there? This is going to be, what we're going to be doing throughout the slides for single neurons, and for multilayer perceptrons, that's exactly what we will be doing. Like the packages that you run in R when you train a neural network are simply looking for the distribution of weights and thresholds that will allow you to get the output that you want to get with the inputs, with the training data that you have. Sometimes you will see, when you check other sources or implementations of packages, you will see that sometimes, the way the information is processed by the neuron is expressed as multiplying inputs by the weights and checking whether it's larger than the threshold. Sometimes the threshold itself is also an input to the neuron with an input value of 1 and a weight of minus the threshold, and then the function is expressed like this. So you check whether this product minus the threshold is larger than 0. It's exactly the same processing. The only thing that changes is where you put the threshold, but it's exactly the same thing. So as I was saying before, right, what does training a single neuron mean? Like, training any of the other machine learning methods or classification or regression methods that we have studied. So training means that, you have this neuron with a set of values and a threshold that you don't know anything about. You start with some values that are random, right? You will assign random weights, a random threshold, but you need to learn what are the weights that are going to take you to the output that you want to get. Okay, and the output that you want to get is basically the difference between what you are predicting and the target output that you have. Okay, it's the difference, as usual, it's the difference between the predicted and the real values. So this training, formally, the way this training is done in neural networks, from a very single neuron, we will see how this translates to sort of more complex multi-layer perceptron settings, right? But, fundamentally, it's going to be very similar. So training with a single neuron is done with the delta rule. And by training, we mean, we have this input data, x1, xn, that we put through the neuron. And we want to make sure that the output y that we get is as similar as we can to the actual labels, to our target output, okay? And so the way we do this is basically by, doing multiple passes. So we pass the training data through the network. We check the output. If the output is not very similar, then we go back and change these weights according to the output. Okay, so we change them so that the next time we pass the training data through the network, we try to see whether this y value is a little bit better. Okay, and we continue changing the weights and passing the data forward, changing the weights backward, passing the data forward, changing the weights backward as many times as necessary until, the error, the difference between our output and the target output is small. What I have just said, you have here sort of the formal definition, but it's exactly the same thing, right? So you have an input x1, xn, okay? You have a desired output O, and then y is your actual output. You pass the data through the single neuron, and if y is different than O, then what we do is that we reevaluate these values, okay? The threshold and the weights are adapted so that the next time that we pass the data again, we try to minimize that error. And what you have here is, that the new threshold is going to be the old threshold plus a change, and the new weights are going to be the old weights plus a change. How do we change? How do we update the threshold? How do we update the weights? So this is basically based on the difference between the output and the actual, sort of desired output that we want, right? What you see here is that the threshold, we do the update only based on this difference. For the weights, we do the update based on the difference as well as on the input values that we are, specifically inputting through that weight. And then this new value, it's just a parameter that we call learning rate. And it's a way that we have for us to control like how much importance we are giving to the improvements of, the new output with the newly updated weights. And so we can also see this delta rule sort of in a code format, okay? And what I want you to look at here, it's basically this for loop. So what you can see here, this is exactly the same thing that I explained in the previous slide, but in a code mode for those of you that maybe read better in code than in actual text. And so you have here a for loop. So for basically we have a training data set and we have the outputs. And what we do is that we multiply the input by the weights. Okay, and we check if that's larger than the threshold. If it's larger, we output 1. If it's not larger, we output 0. So what we are doing simply is this feed forward pass. We take the input, multiply by the weights, and then the neuron says, is it larger or smaller? And we output a value. Now, what do we do? If the value is different from the output, okay, or is not good enough for us, what we do is that we go back and update all the weights and the threshold. How do we update them? We update the threshold based on the difference between the actual output and the output that we want. And we also update the old weights based on that difference, but multiplied by this input. Sort of, the new weight has to be changed in a way that we take into account the errors that we made when we inputted that through that arrow, okay? And we basically do this until the error is smaller than a given value that we want, okay? You will sometimes see, when you read about single neurons, that some people talk about online training versus batch training. The only difference is that the online does sort of this feed forward, back forward process for every sample, whereas the batch training basically only changes the threshold and the weights after all the training samples have passed. Okay, so this is the delta rule, but from a batch perspective. The only change that you see here is that the update of the threshold and the update of the weights is basically done after all of the samples have passed through the network. Okay, this is just another way of implementing things. When you read about, different packages that you're using when training your single neuron or multilayer perceptrons, you will see that sometimes they will refer to online or batch training. But it's just that small difference that, whenever, the output is not similar to the desired output, you sort of compute, changes for the threshold and the weight, but you don't update those until you have passed all the samples through the neuron. And then, in talking about single neurons, there is sort of this one very well-known single neuron model that's used a lot. It's called the Makula-Pitts perceptron. Okay, and the main difference with respect to what we have seen is basically this activation function. So far we've seen it all, right? I mean, we have inputs, we have weights, we have the threshold as an input as well. We compute the summation of everything, and then we sort of, output a y value depending on how that summation is larger and smaller than the threshold. So the only thing that the Makula-Pitts perceptron does is that, it passes all these product of weights and inputs, passes it through what we call an activation function, okay? The activation function that we have seen so far is a threshold function. So if you see this epsilon, basically, as this is a net sum, it's the product of weights and inputs. So, so far we've seen a case where, you look at the product. If that product minus the threshold is larger than 0, we output 1, otherwise we output 0. This is what we've seen so far, right? By using the threshold, we output one thing or the other. But oftentimes what happens is that net sum, that product of the weights and the inputs, is sometimes passed through a sigmoid function. So the difference is that, with a threshold function, you only have two outputs, 1 or 0. With a sigmoid function, the output of your neuron can be any value between 0 and 1. And this is very useful when we are, for example, talking about regressions, right? And so oftentimes you'll see the Makula-Pitts function, a neuron, but also other models will use this sigmoid function because it basically allows us to output values between 0 and 1, okay? There's also sometimes a hyperbolic tangent used where, the output is going to be values between 1 and 0. But again, the only difference here, it's exactly the same model. The only difference that we're doing is that, the product of the weights by the input is passed through a specific function that's going to squash those values either between 0 and 1 with the sigmoid function or between -1 and 1 with the hyperbolic function. Okay, and then just to finalize this single neuron training and the delta rule, as I've said before, if we work with Makula-Pitts, which is generally what we work with, we generally work with an activation function that's of the sigmoid type. Basically, how do we apply the delta rule? Well, the delta rule is applied exactly the same way, right? I mean, you pass all the data that you have, you look at the output, and then you transform or you update the threshold and the weights, right? However, what happens is that when we look at the output, in our case, the output is basically the product of the weights multiplied by the input, and then basically, we look at whether that product is smaller or larger than the threshold, and we output a specific value. That value, we look at whether that value is very similar or very different from the target output that we are looking for, right? And so what we want to, the reason why we do this training is because we want to minimize the errors that the single neuron is making when predicting the output value, right? And so to minimize those values, means minimizing, this sigmoid function. Again, remember that for the Makula-Pitts, the product of the weights and the input, which is this epsilon, right? This product is passed through this function. And so in this case, minimizing the difference between the output and the target is not just minimizing a difference, but it's rather minimizing this sigmoid function. And the way we minimize this is using the gradient function and basically applying the derivative of this function and making it equal to 0 and finding, what are the weights and the threshold that allow us to get there. And so what I'm trying to say here is that when we look at the errors that the single neuron is making, in the case of a single neuron that uses a sigmoid function, we need to multiply those errors by this value, which is the derivative of the sigmoid function, right? And so basically the delta rule is transformed as follows. If we take sort of the batch approach, for example, when we update the threshold and when we update the weights, it's not just updating them by the difference between the output and the actual value target, but it's also taking into account that update, okay, needs to take into account this derivative value, okay?